Hi everyone, welcome to MathSpellBook. I'm your host Pete, and we are here basically to discuss eigenvalues and eigenvectors. So hopefully you guys won't mind if we also have a guest with us. So I'm going to bring Sascha in for us. So just give me one brief second while I bring him into the chat. But how are you guys doing? If you guys are watching this on YouTube, if you like math and physics, consider, hitting the sub button as well as hit a like and a comment down below. And also, if you're watching this after the live stream, I've put Sascha's Twitch channel in the description down below, so check out his Twitch channel as well, because he started streaming, and hopefully we can get more people to follow him, because he is very knowledgeable on math. So hopefully you guys will be able to appreciate the knowledge he has to share. So I will bring him in. Hey Sascha, you're in the chat now.
Hey.
How you doing?
Good.
Okay, so the floor is all yours.
Alright. So today we're going to talk about eigenvalues and eigenvectors.
Okay.
So first of all, I just need to make sure you know some stuff in linear algebra before I start, because otherwise some stuff might not make sense. So
yeah.
You know what is a basis, right?
So my I feel like I'm familiar with it. The thing of it is that, like, the way I explain it, so this is my way I would think of a basis in my mind, and you can correct me on the details. So the way I think of a basis, oh, that is way too...
That's thick.
Yeah, that's way too thick. So, here we go. I don't know why it always changes. So the way I think of a basis is that I would think of it this way, where it's like, let's say it's just A, and then like we have like U1, and then B, E2, something like that. Like, this is just an example. I would think of a basis vector as sort of like this, and I think like basis, I think the way you're talking about is like the span. If you guys don't know what span is, it's basically like how many of these guys are in this particular, I guess you can say, set or space. And I think that's the way my brain goes about it, but you can correct me on the details if I got something incorrect in the interpretation.
I mean, you seems close. So, okay, I will just give it the definition in general, but the important thing was the thing you wrote, right?
Yeah.
For all v in our vector space, little v, I usually just write little letter for the vector here. I don't put arrows on it. You're able to decompose any vector into your basis, right?
Yeah, and I will like interject, like, this is the way I would think of a basis vector. And so when you ask me, like, do I know what a basis is, this is what comes to my head.
Yeah, but the important part is that any vector inside of V can be written as some kind of combination of our vector, right? Actually, this property would just mean that our vector E1 and E2 would generate V, but actually we want this decomposition to be unique.
Okay.
Okay?
Yeah.
So for example, the standard example, if we take V to be equal to R2, and we take the standard basis, which is just the basis you obtain by just putting some 0 and 1 in some coordinates. Okay. This would be a basis because you can, I mean, if you take any vector inside of R2, it would look something like that, right?
Yeah. And they just coincidentally are also unit vectors.
Yeah. And you can write something along those lines, right?
Right.
And you know the coefficients are unique, because otherwise you wouldn't get the right coordinates.
Right.
But another example would be, okay, let's take V to be equal to R2, and take E1 to be equal to 1, 0, E2 is equal to 0, 1, and let's say we have even a third vector, which is 1, 1.
Okay.
And so here we don't have issue. In the same sense, we can still write any vector AB as A times 1, 0 plus B times 0, 1, and then we can just put the 0 for the other coordinate, for the other vector, right?
Right.
This will still work, right? But the problem now is that this decomposition is no longer unique. Because, for example, we can write the vector 0, 0 in a multiple way now. We can write, well, first of all, we can write the trivial way of writing it, just putting a bunch of 0 on all coefficient. That's one way of doing it.
Yeah.
And the other way we could do it is to be, for example, putting some -1 on the first two guy, and putting just a 1 inside of that. So as you can see, we have two ways of writing the 0 vector as a combination of our basis. I mean, of our 3 vector that we chose. So therefore, the decomposition is not unique, right?
Right. Yeah.
So E1, E2, and E3 are not a basis.
Because for it to be a basis, like I think like the amount of unique vectors you can have is just like the same amount as the dimension, right? So like for for E1 and E2, it would make sense for R2, but if we had like V is equal to R3, then basically E1, E2, and E3 would be a basis, right?
Yeah, we will have to change. So for R3, we would need to. I mean, so okay, if we use, for example, in R3.
Yeah.
I don't know if that's what you had in mind, but something like that.
Because I remember the amount of dimensions also tells you how much unique vectors you can have as the basis.
Yeah. So that's exactly the definition of the dimension. The dimension of a vector space is the cardinality, so the number of elements inside of a basis. That's exactly the definition of dimension. And actually, you have to do a little check to make sure that if you pick another basis, if you to make sure that you don't like the number of vector doesn't change.
Yeah, because they have to be linearly independent, correct?
Yeah. Yeah, that's pretty good. So okay, maybe if I go to the non-example I gave earlier, the problem here was that the uniqueness part of a basis failed because we didn't have linear independence between our 3 vectors. That's what failed us. So in R3, is that the example you had in mind for R3?
Yes. Like so like the reason why I think like when you replaced A and B with 0, 0, right? You basically said it's not unique because there's so many ways to actually get to that vector, and that doesn't. And the basis vectors, they shouldn't do that. Like basically A and B should be like, or the coefficients in front of the basis vector should, in order for them to be linear independent, in order for us to get 0, we have to make sure that that A, B, and C, which are the coefficients in front of those vectors, have to be at least equal to 0 if for that to happen. Yeah.
And so the third example here wouldn't be a basis there for multiple reasons. First of all, we can sort of copy what we did before with the same coefficient.
Right.
And also, I mean, it's pretty easy if we just look at what our vector we chose. None of the vector we chose has a non-zero entry in the third component, right?
Yeah. Just to catch you up, Sascha, I'm currently on the section of transpose. So, like, the section I'm on is like on transpose involving null space and like its relation with column and row vector row spaces. So that's where I'm at. So.
Okay.
Just to let you know.
Okay. I mean, that's pretty good. I think we will be able to cover what we want to cover then.
Yeah.
Okay. You seems pretty. I mean, you seems pretty okay with basis, so I think we can move on. Okay. And okay. And you heard about the linear map, right?
Linear maps, I'm familiar with it. I just don't fully understand it.
Okay. Now I will do a connection, which is probably the most important connection to do in linear algebra, is that actually linear map and matrices are exactly the same thing.
Right. Okay.
So I will show you a little bit how it works. So let f be a function between two vector space.
Okay.
Where v and w. I mean, we're gonna take them to be real because.
So it's not no complex numbers here. It's just all real numbers.
Yeah.
Okay.
Oops, vector spaces.
Yeah, the way I'm starting to think about matrices now, because since I'm kind of understanding linear transformations, is that I would think of matrices as the space, and I would think vectors as sort of like, you know, the forces that act on the space. Because when I saw like how linear transformations work, I was like, oh, if I think of matrices as sort of like the space where the vectors behave in, it makes it so much easier for me to actually understand better how a linear transformation works.
Yeah. Okay, so I will show you. So I will just give you the definition. So we ask that for all little v1 and v2, and we ask for all scalar lambda inside of R. We want that f of v1 plus lambda v2. So we want f to preserve a multiplication by scalar and addition. So we will ask for this condition.
And f itself is a vector space?
So f is just a function.
It's just a function? Okay.
Yeah. And usually the easiest example you can sort of think about will be something like so let's take v is equal to w, and just for simplicity, let's both be equal to R2.
Right.
And then the limit map would be something like I don't know, we could do something like 4x plus 3y.
Okay.
And I don't know, maybe we can put x minus y, something like that. Okay.
Yeah.
And the point is that if you have a basis of your space and you have a linear map, then so first of all, usually function, for example, from R2 to R2 can be quite complicated, right? Because there's like infinite stuff, there's like infinite amount of stuff to keep track of, right?
Right, yeah.
But because vector space has basis, and basically everything can be written as linear combination of our basis, and linear map preserve addition and multiplication, then basically linear map will be completely basically linear map would be completely determined by how a basis work on them. Okay. So maybe I will just do a little bit of manipulation, and then we're just gonna check it. Okay.
So, like backtracking on what you said, right? You're basically saying that the function that we have right here, that would be like in linear algebra terms, that would be considered as a linear map, right? So
yeah.
So basically, a function is basically a linear map is basically a function within linear algebra.
Yeah.
Okay.
That preserves the operation of our vector space, namely addition and multiplication by a scalar.
Okay, so my question to you is that since it's actually working in R2 in this case, or an example, right?
Yeah.
So basically, does the linear map, how does that relate back to a linear transformation?
So linear map and linear transformation are the same thing.
They're the same thing? Okay.
Yeah.
So should we think of like the way I gave you my example before on how I would think of linear algebra now is like basically I would think of the matrices as space, right? And usually when we think of a linear transformation, we would think of some matrices multiplied by some vector, right? Whether to get the zero vector or whether to get some other vector, right? So my question to you is that would thinking about a linear map the way I think of a linear transformation, would my thought process on thinking of a linear transformation still fit with a linear map, or would a linear map be more detailed in like its definition? So
linear map and linear transformation are the same thing, but at the same at the end of the day, they're just like mapping space, like it's just a map between two spaces.
Okay.
And you will see that basically the reason that because we have basis and bases are finite,
yeah,
and linear map preserve basis,
yeah,
preserve at least linearity. we will get that basically those maps can be represented by a very small amount of numbers. Okay.
Okay.
So I will just do an example. So let I will still use the same notation I used before. So let v. So let e1, en be a basis. For v. Okay.
Okay.
And so let's take v to be an arbitrary vector in v. Okay.
All right.
Because we said that e1 to en is a basis, right?
Right.
It meant that v can be written uniquely as a linear combination of the bases, right? Maybe I should put my indices because otherwise I will be sloppy. So where AIs are real. All right.
And these are just regular subscripts, right? They're nothing to do with covariant or quadravariant.
No.
Okay.
No, just some indices.
It's just an index. Okay.
Yeah. And if I apply f, which is linear to v, then what I can do, I can use the decomposition I just introduced before. But now, as f is linear, it means preserve addition, right?
Right.
So it means I can put the summation sign outside of the function.
Okay.
Right.
Right.
And I mean, it's a linear, so it's also preserve multiplication by scalar, so I can also put the AI outside.
Right. But it's still contained within the summation symbol, right?
Yeah.
Okay.
And what you notice here is that I started with an arbitrary vector. I just took any vector inside of V.
Right.
And what I got at the end is just a linear combination of my bases, right?
Right.
Where my basis was mapped to, right?
Yeah.
Okay. But then here it's a little bit complicated to see what's going on because FA can be it's just a vector inside of W. We don't really know what it is. So why not just pick a basis on W as well? Okay, let's call it B1 to be M. Okay. So V and N can have the different dimension. One is dimension N and the other is dimension M. Okay. So in this case, so F or I will be a part of W, right? So as we have a basis on W, we can decompose this guy as well, right? I will use J instead of I for that, but...
what's the reason for that? Is that, is it a different basis, or is it, just out of convenience?
You do it out of convenience, because after that it will make my life a little bit easier.
Oh, okay. But,
okay, and this guy...
But we're treating EJ and EI as the same thing. You're just basically making it convenient for yourself to write, right?
Yeah.
Okay.
Just a dummy indices so I can change his name.
Okay.
So this guy, we're gonna call it... Okay, I called this guy AI, so maybe it was not a good plan, so let's maybe call it M.
Okay. That's fine.
MIJ, and then now we can write it in terms of the basis, so it's gonna be BI, right? Okay, did I do something stupid? No, I think it's fine. Okay, I think it's fine. Okay. So if we go back to... Oh, I got an error. Okay, if we go back to the formula we had before and we use the thing we just learned, and maybe I will just switch my... So I will maybe use this formula, but I will replace the I by the J instead. I will get that f of v is equal... So I will just write the thing we had before, is equal to J1 up to n of AI, AJ, my bad, and then f of EJ, but this is given by this formula, Um, well, okay, maybe I will just do it in 2 steps. So I will first write f of ej, then I will just use the thing we just covered there. So, okay, that's a horrible.
A horrible sigma. It's fine.
Yeah, it was pretty bad. Now we're gonna have 2 summation. AJ BI. Okay.
Alright.
So we can, I mean, it looks complicated, but we just kind of took the 2 things we were kind of simple and put it together.
Alright, so backtracking. So you wrote you wrote like let B be a base. Let's be a basis on W, right? So
yeah,
B is basically like everything. So W basically encapsulates everything that's B, and B is a basis from W, right?
Yeah. So the B's are a basis for W, and the E are a basis for V.
Okay, so like for E, basically, like I'm guessing because we're going from V to W, right? That's why you wrote that second part where it's the double summation with AJ and IJ. Okay.
Yeah.
All right. What's next?
All right. So what's next is, you see these guys?
Mm-hmm.
I mean, maybe we can just go maybe a step before.
Mm-hmm.
The MIJ here.
Yes.
It has double indices, right?
Right.
And how many of them are they?
There's 2 of them.
Yeah, but I mean, like, on like what value can I and J takes?
Practically like an infinite amount. Because we're
not really, right?
Oh no, go up to M. It will go up to M.
Yeah, I will go up to M, and J is indexed by the basis of V, and those we know we have N of them, right?
So I think for J it can go up to N, and I think for I it can go up to M. I mean, based on what you wrote on the summation symbols.
Yeah, so I is stuck between. Oh, it's not. I don't know if that's what you said, but I is stuck between 1 and M, right?
Yeah.
And J is stuck between 1 and little n, right? I mean, that's basically what. Yeah, it's basically what you said. I just wrote it in the end.
Yeah, I saw the summation symbols and I thought, oh, okay, that must be what you meant.
Okay. Mm-hmm. And let's now write a matrix who has this as entries. Okay.
Okay.
So maybe we're gonna call it M, and it's just gonna be the matrix given by M11, M12.
And then we're gonna put the dotted lines all the way to like M something.
So okay, so we said that J goes from up to N, so this guy will be an N. Then we're gonna have M21, M22,
Yeah.
M2N, and then at the end we're gonna reach what is it? Okay, that's kind of cursed to use M and M for the... It's okay.
It's fine. We know it's subscripts.
Yeah.
And then at the end it's gonna be M to N, M, N.
Yeah. And okay, maybe there's a couple of things we can use using the formula we just derived. Is first of all, let's have a look at this formula.
Okay.
Okay.
All right.
So okay, let's have a look at this formula and let's put J is equal to I don't know 1. Okay, just for simplicity. So if we put J is equal to 1, so maybe I will just write it below. We're gonna get F of E1. This guy will go. Is it 2M? N. It's 2M. Okay.
Yeah.
So it's gonna be MI1.
Right.
right? Because we fix j is equal to 1 of b I.
Okay.
So what it said okay, the second entry is fixed, and the first entry can move up. It can move freely, right?
All right.
And if we look at our basis, if we look at our matrix, what does it represent? Like what? Do you see where this thing show up?
It would practically, so since like j is 1, basically, and 1 is fixed, so it will only lead us to the first column, and everything within the first column will lead us to the summation there.
Exactly. So the first column is exactly the image of our linear map F. Written in our basis EI and BJ, right? Like if we just focus on this part, okay. The coefficient you see in the row, right? For example, M11, M21. All the coefficients you see in the row are just the coefficient that go in front of the BI, right?
So, like.
So you can.
Is the m's considered like the coefficient that goes in front of the basis, which is b?
Yeah, exactly. So maybe I can write it here. But on the left, you sort of want to think that you have the basis. So what is the first column of the matrix saying is that the first vector, so the f of E1 is equal to M11 times B1, M21 times B2, and so on. Okay. Now, what do you think happen if I change J to be something else? Let's say I put J is equal to N.
Well, it would basically be in the nth row, or the nth column.
Nth column. Yeah. And there's nothing special about
the columns
of 1 and n, right?
Yeah.
So all the guys, all the column of our matrix are just the image of our basis. Okay. And basically, when you read the column, you just read the coefficient of those linear combination.
Okay, so my question to you, right?
Yes.
So since we're doing by column, right? I know this is getting into much more complicated stuff, but I remember looking up covariant and quadravariant, and I would think usually I remember that covariant is like the lower is the subscript, right? And quadravariant is the superscript. So if we had like basically instead of like a subscript what you wrote for I and J, and we had it as a superscript, would that mean we would have to take the rows instead of the columns at that point? So when it's called raising the indices. That's not exactly the same thing. Yeah.
I mean, it's a special notation we use, so it can either mean usually raising the indices, usually you need a scatter product or something like that to do raising the indices. So we don't have any of that, so we don't. This doesn't really apply here.
Oh, okay. So what would since we have it with just the columns right now, right?
Yeah.
And I'm guessing because it's math and we love symmetry, what would we need to do in order for it to be the rows and the basis vectors to be like multiplied by the row components instead of the column components? Because we do have column space and row space.
Yeah. So so for linear map we usually just work with the column, but the row, if we swap the column and the row, we get something called which is M transpose, right?
Yes.
But okay, this is not very helpful because that's just like we just flip a bunch of number, right?
Okay.
It doesn't really tell us what it's supposed to mean geometrically, right?
Yeah, I think the reason why I asked is because since we have the summation symbol, what circumstances do we need for doing, I guess, like, why is it column? Like, why isn't it not rows? Like, it's like that question where it's like, have slope, and you're like, why is it rise over run instead of run over rise? That's why I'm asking.
Okay, I just want to add a little thing, okay?
Yeah.
Okay, the second thing I wanted to show you is that this tells us the story for when we're looking at the basis, right?
Mm-hmm.
But if we want to look at something which is not a basis but just a linear combination of it, for example, a vector v which is AJ, right?
Yeah, I think it's like J.
I mean, if you look at the form with the error I have here, okay, maybe they will need a little bit of play with it with some low value of n and m to see what's going on. Maybe we're going to do that after that. What you're gonna see is that actually v is given by our matrix m times the coefficient here.
Okay.
I should put the f of v, sorry. So computing the image of a vector by a linear map is the same thing as applying our matrices M to the column vector obtained by the coefficient.
Now, I think I'm sort of familiar with because I remember seeing this in a book. Like we probably might not cover it, but I remember something with this, and I think it's like a piecewise function, where it's like if I is equal to j, I think it's supposed to be like and if I is not, it's like what's equal to 1? I forgot what it was called.
So it's 1 and 0. It's called delta, Dirac indicatrice function.
Yeah, like is this
delta function.
Is that involved here? Because like we have the summation, or is this like a particular instance where it's like symmetric?
So I mean, there's a lot of use for this guy. So it's more like just a notation, like stuff.
Yeah.
For example, you see the identity matrix. Maybe I would call it I. I can just say its coefficient are delta ij, right? Because when I and j are equal, it means that we're on the diagonal, right? And we know that the identity matrix is just something like that looks. You just have a bunch of 1 on the diagonal and a bunch of 0 everywhere else, right?
Right.
So for example, we can use that.
Okay.
I mean, it's also involved when we talk about draw. Okay. So so evaluating a vector to our linear transformation is equivalent to apply our matrices to a column vector with the adequate coefficient, right? And now you ask, why are we doing with the column, right?
Yeah.
The answer is that it doesn't really matter. We could do it with the rows, but instead, if we want to go with the rows, we would need to multiply this guy from the left instead.
Right.
And look it as a row vector instead of a column vector.
Right.
But it's more like just a taste of notation. So we usually work with column instead of row.
Okay.
Yeah. Later on, if we want to talk about it a bit more, I can actually give you what is the linear algebra meaning of taking the transpose of a matrix. It turns out that taking the transpose of a matrix is basically looking at the dual of a vector space.
Okay.
With some kind of dual basis.
Because I think if you take the column space of the transpose, you end up getting the row. I think the row space of the original matrices, or like or was it the rank? I don't remember.
Yeah, the rank is supposed to be the same for the row and column. Okay, so we have that. Okay, so maybe we're just gonna look at an example. Okay, usually when you want to do computation, you work with the standard basis, and if you need to change to another basis, you then do some change of basis matrix, which we're gonna cover maybe later on. But let's take our example we had before, okay?
Okay.
Maybe I will just... I will probably not take exactly the same example, but I will take something similar, okay? So F is a map from R2 to R2, okay? And, okay, here I'm gonna take something very simple. I'm just gonna take... I will just equip R2 with the same basis, okay?
Okay, like before you continue, Sascha, on YouTube we're being visited by SSJ Seiyan. Love the name. Good evening to you. It's basically good afternoon from me. Can you please tell me what is this? So this is linear algebra. So Sascha is actually teaching us about eigenvalues and eigenvectors. So that's basically what we're going through so far. But how are you doing, Saiyan? How are you doing? Like the name, because I'm a big anime fan, so I know probably why you have that name. But go on, Sascha.
Okay, so I chose my basis E1, B1, and E2, B2 to be exactly the same thing. So E1 is equal to B1 and E2 is equal to B2. Okay. Which is the standard basis. You will see later on when we talk about diagonalization that usually the standard basis is not usually the best one. For some matrices, there's like better bases that make our life simpler.
Okay.
But usually when we do computation like that, we prefer using a standard basis. We just need Okay. And I will show you how we build the matrix associated to F. Okay.
Okay.
Let's build the associated matrix. Okay. And here I just want to stress the fact, okay? When you talk about a matrix and you want to see it as a linear transformation, you don't just need a linear map, you also need a basis.
The basis.
Yeah. If you change the basis, then the matrix will change, okay? So we have to I mean, sometimes people will write, like, for example, EB for saying, oh, that's the matrix of F computed in the basis of EB, okay? But we will not do that because I don't really like to...
So, like, before you go on, because, like, since you actually have a concrete example here, I think I have an idea of what you're trying to do. So, so since we have a basis, like, for 1, right? For E1, right? So I'm guessing we implant this into these. So basically we have 1 plus, so since x is 1 in this case, and then we have 0, and then for the bottom we have, that's a y, right? X minus y.
Yeah.
So it's like that, and then that's going to be like one of the rows.
Yeah, exactly.
And then the next row would be the second basis, which is basically the same thing. So it's like dot 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 dot, and basically 0 minus 1, and then it's going to leave us with 2 minus 1. And I think the matrix or the transformation that we have is this, right?
Champ, you did your homework, my friend.
No, because like when in my linear algebra course that I'm doing online, it covers that, and I was like, oh, that's what it's supposed to do.
Yeah. Okay. So you're already like a champion.
No, I just remember, like, it just looked familiar to me, and I'm like,
yeah. It's exactly that, yeah.
The one thing I was worried about is that I wasn't sure if I had to write it as a row, like, so 1 1 as a row instead of a column, and I was like, maybe it's a column because the way it's set up, so I'm like, okay, we'll just go with column.
Yeah. So the column is just, so the first column is just the image of F10, and the other guy is just F01.
Okay.
And the row is just our basis, so what is it, B1, B2? So yeah, it's exactly what you wrote.
Okay, so, because the thing of it is that the one thing I'm wondering is that, let's say if F, because, like, when we think of F, right, as a linear map, right, because you see how I did it as a column? What is, stopping me from actually doing it the opposite way, where I can make it a row? Like because I think I did that because I just saw it in like the example I did, like in my linear algebra course. But what will tell me that I have to do it as a row instead of a column? That's my question to you for the linear map.
So I mean, as I said, we can just, I mean, okay, if we have like M or I mean, we could do it with rows.
Yeah.
But we would need, so you know, so for example, when we apply a linear map to a vector,
yeah,
what this corresponds in the matrix wall is this, right?
Yeah.
But if we want to do it on the row, there's nothing that stops us to doing that. But instead, if we want to have the correspondence between linear map and matrices,
right,
we will need to use V transpose and use, I think here do we need to take M transpose? Maybe. We would need to do something like that.
Oh, because it's basically like, because now I'm remembering how matrices have like row and column, but you actually have to have a rule where it's like, the column, the row, the column in the first part has to match with the row in the next part.
Yeah. Yeah, there's like a dimensions 90 you have to do. Yeah.
Right. Okay. Yeah. Now that makes more sense.
Yeah. So you can do it with row, but the only thing is that you have to multiply it from the left.
Yeah, you have to switch it around because you have to make sure it's symmetric in that way. Yeah.
So usually people prefer to multiply by the right, because usually when we write functions, we evaluate
that way.
Yeah. I mean, yeah. Okay. Okay. Okay, that's good. Okay. Okay, maybe I will just write some stuff. I mean, I will not talk too much about it, but I will just tell you a little bit more about the correspondence. So, as you said, as you saw, we have a correspondence between linear map and matrices. Okay. So a linear map F on V to W will correspond to a matrix, right? So for function, I can compose them. If I have like two linear, if I have like, for example, F that goes from V to W, and J that go from G will go from W to, I don't know, E. Then I can form a new linear map, which is G composed with F, G after F.
Okay.
And this will be a map from V to E, okay?
Thank you, Academy, for the raid. We got raided, Sascha.
Yeah.
So the lecture hall is getting full. Welcome, raiders. Welcome. I am Peter, aka MathSpellBook. Hopefully you guys don't mind checking in on basic linear algebra with us. Hope you're having fun learning linear algebra. Some of our friends want to learn more linear algebra. Oh, okay. Just sit back, relax. We're learning more about eigenvalues and eigenvectors. So hopefully you guys will enjoy. Go on, Sascha. Sorry.
So linear map correspond to a matrix if we fix a basis. So let's say F correspond to a matrix M. And if we have two linear map, then we will get two matrices, right?
Right. Yeah.
So it's going to be N and M, right? And one thing we should ask is, what does the composition of linear map correspond in the matrix well? Well, okay, let's say that's okay. Maybe I will. Maybe I should use.
Because it would probably function the same way like a composition with functions work, right?
Yeah, but this corresponds actually to matrix multiplication.
Okay.
Actually, if you look at matrix multiplication, that's kind of thing you have to unravel though to see it. But basically, you have to tell yourself that matrix multiplication is designed from the ground up to be the composition of two linear map. That's why like the multiplication is so weird, is because the motivation behind it is it wants to replicate what the composition of function does.
Which is basically just taking one big function and just putting a small function within it and
Yeah.
Like it's kind of like
Taking the input on the first one and then having the output and feeding to the other.
Yeah, it's like the function that's outside basically eats the small function, but in this case it's not that. It's basically you're just multiplying two matrices together.
Yeah. And the reason why and the reason why matrix multiplication is so weird is because it corresponds to that.
Yeah, which is I can see why that seems strange, because it's sort of like with functions we do something different, but with matrices we don't do that, which is kind of strange. I think for me it's like since I view matrices as like space, it's like you're taking two spaces and putting them together in some way. That's the way I would probably think of it, which actually this kind of makes more sense to me, but then again, like functions are a bit more complicated when it comes to that.
Yeah. So basically linear map can be understood from two point of view. First of all, you can sort of think of them as a function, which preserves preserve the operation of a vector space. And if you take a basis, you can think of them as matrices.
Right.
Okay. And so the first one is kind of good because we can understand. I mean, the first one thing which is cool is it's independent of bases. Okay. So if we define something for a linear map, then it's kind of, I mean, and we don't use bases, then the definition is independent of a choice of a basis. A matrix on the other side is kind of a little bit more annoying because you have to pick a basis, right?
Right.
To make sense.
Okay.
But one thing which matrices are good is they're good for computation. So for the theory of eigenvector and eigenvalue, I will sort of switch between the two back and forth. Okay. Usually it will be easier to define definition, for example, of eigenvalue and an eigenvector using linear map, but usually the computation will be carried on matrices. Okay. So matrices are you sort of have to think that linear map is really the real linear algebra concept, and matrices are more like a screwdrivers to do the task. Okay, it's just like a tool for computation. Okay. So I will give the definition of eigenvalue and eigenvector. Okay. So eigenvalue or eigenvector are looking at very special map. Okay. So before we were kind of saying, okay, we have f, we go from v to w, right? Where v and w can like be a different vector space. I mean, they can be whatever they want. But for eigenvalue and eigenvector, we will restrain ourselves to linear map that go from a vector space to itself. Okay. Alright. So maybe I will just give you a little bit of terminology. A map, maybe a linear map. F that goes from V to V is called an endomorphisms.
An endomorphism?
Okay. Yeah.
Okay.
Which basically means map to itself. Okay, that's kind of a Latin word. Endo means like to itself, and morphism is like transformation.
Is that also similar to with functions? Like
yeah. So sometimes we will call a function morphisms.
Okay.
But they're called endomorphisms.
So if it was f from v to w, right? That wouldn't be an endomorphism then, right? Because yeah. Okay, gotcha.
So it's a map to itself, okay?
Okay.
And so what we're gonna do? So we're gonna define eigenvalue and eigenvector, and you will see the definition is quite simple. Okay.
All right.
So the definition is that we say that some scalar lambda in R is an eigenvalue.
Okay.
If there exists a vector v inside of big V. Also, we need some condition because otherwise the thing will already clarify. We need to assume that v is not equal to 0. Okay.
Okay.
Otherwise, the condition I will write here will be trivial.
right.
And what we ask is that, yeah.
Oh no, I will be right back, Sascha. Just hold that thought for a brief second, okay?
Oh, okay, yeah, that's
All right.
fine.
All right, I'll be right back, guys. Just give me 1 second. All right, we're back. Carry on, Sascha.
All right.
Sorry about that.
All right, and basically we're gonna ask the simple thing we could ask. So a map, which I mean, usually linear map can be very complicated. They can map a vector to a very complicated stuff, right?
Mm-hmm.
And eigenvalue and eigenvector is gonna be like kind of the simpler thing they can do.
Mm-hmm.
So what f gonna do to v is just gonna scale it by our lambda, okay?
Mm-hmm.
And we call such a v an eigenvector associated to our lambda. Okay.
Okay. We call such a v an eigenvector associated to lambda. We say that lambda is an element of the real numbers, is an eigenvalue. So the eigenvalue is lambda?
Yeah.
And the
V
vector
is
is
an
v is
eigenvector.
eigenvector. Okay.
Associated to lambda, yeah.
Alright, okay.
And so what is cool with eigenvalue and eigenvector is that f is quite simple, right?
Mm-hmm.
Applied to them.
Okay.
So if we have an eigenvector and an eigenvalue, the f is not easy to compute. Like it doesn't do crazy stuff, it just rescale our vector, right?
Mm-hmm.
On such vector. Okay. And now the thing that we're gonna care about is let's assume that v has a basis given by the I shouldn't put d, I should just say pi. Given by so the basis is constituted of eigenvector of f, okay?
Okay.
So in other words, so maybe we're gonna call this basis, I don't know, e1, and be restricted up to en.
Mm-hmm.
So it means that we have f of ei is equal to lambda I ei, okay?
Okay.
And now what I want to do is that I want to compute the associated matrix to such a linear map with this basis.
Okay.
Okay.
Uh-huh.
So I mean, okay, maybe I can. Okay, maybe we can do the computation together, but it's not really hard, right?
Okay.
So our matrix will look something like that, right? We're gonna have f of e1, f of e2, up to f of en, right?
Mm-hmm.
And on the column, on the row side, we're gonna have our basis.
Mm-hmm.
Okay. And then what we said earlier about the matrix associated to a linear map. So the first column should be the image of a vector, right?
Right.
So what will it be? Can you fill up like the first two columns for me?
Okay. So let's see. So in this case,
You don't need to put the E1. It's you just need the coefficient, so you will just put the lambda 1.
Oh, okay.
But you're on good track, yeah.
So,
Are you sure it's lambda 2, right?
oh, whoops! I forgot the other indices. So B1, 1, right? Oh no, it's not double indices. Because technically this would be the first column, but in the second row. So this would be. Now the thing is that I don't know if I have to use double indices for this.
Okay, I will help you a little bit, okay? Let's do E1 together, okay?
Because I feel like I have to use double indices.
No, you wouldn't have to. Okay, let's look at E1, okay?
Okay.
So if we just use the formula little star that I put there, we're gonna have for E1 something like that, right?
Right.
Do you agree?
Yeah, because then like basically E1 is the basis and it's multiplied by lambda 1.
Yeah. So therefore, this is a linear combination of E1, right? So therefore we can write lambda 1 E1 plus I guess we're gonna start at 2 up to n of 0 times EI, right?
Uh-huh. 0 times EI, okay.
So I mean, okay, maybe I can write it maybe a simpler term. So in another sense, all the coefficient in front of the other coefficient are 0, right?
Right.
That up to 0 times En. Do you agree with that?
Yeah.
Okay. Therefore, the first column should be the image of a E1, right? Under a basis.
Yeah, so it would all be like lambda 1 in that case then.
It will not be lambda 1, right? Because so if we look just at the first column, okay, the row that goes here would be those coefficients here.
Oh, okay.
It's just basically, it's probably just because the example is a bit abstract, maybe, but before you did like
so going by that pattern, like I think I just didn't understand the question. That's why I think I didn't get that correct. So
yeah.
So if that's the case, then they would practically be like all 0 until like at that point, right?
Yeah. And what is cool is that you will
it's
get
a diagonal.
Exactly. It's diagonal.
Someone in our chat, Zumba typed, I think it was like image of E1 equals, I think that's vector lambda 1, I think. I don't know exactly what that's supposed to mean. I don't know if that's a joke.
So if we're able to if you have a linear map, which is an endomorphisms, and we're able to find a basis makeup of eigenvectors of f, then we can have a very, very simple way of writing our matrix as a diagonal matrix.
Okay.
And this, for example, for computation, can make our life very easy. Because, for example, if M is a diagonal matrix, maybe I will just put something very simple. Maybe I will put a 2x2 matrix. Then, if you want, for example, to compute, I don't know, M square. I mean, if it was a general 2x2 matrix, you would have to do the multiplication for all the entries, and it will be very complicated. Okay.
Okay.
But for diagonal matrix, it's quite easy. You just square the component wise. Yeah?
Okay.
Yeah, on the diagonal. Yeah. And you can do that for, I mean, there's nothing stopping you, but you can do it for k instead.
Oh yeah, because I think I've read this in like one of the linear algebra books. It's like, how do we actually square a matrix? And if we, or take any higher power, it would be very complicated if we had to do it, because it would be like a matrix times a matrix times a matrix. Yeah. Okay.
So if you have a diagonal matrix, it's very easy computation. And when you want to do ODE, system of ODE, you sometimes want to compute the exponential of a matrix, and usually it's kind of a similar mess that you run into.
Yeah.
But if the matrix is diagonal, then it's the most easy thing to do. You just raise the diagonal as an exponent as your exponential. So for computation, diagonal matrix are very easy. Okay. And I mean, okay, so that's kind of a route we could do. I mean, that's one of the applications of diagonalization, is that you can compute those kind of things. And for example, computing the exponential is very important because it allows you to solve a system of linear or linear differential equation. Okay.
Okay. So one question I have is that when it's like eigenvectors and eigenvalues, right?
Yeah.
Does the eigenvalue and the eigenvector always have the same index, or is it like they can change indices?
So usually, what people do is that they index the eigenvalue by the eigenvectors. So they will write lambda 1 is associated to E1, lambda 2 is associated to E2. Okay.
Okay. Is that the only way to get the diagonal?
I mean, it's just a notation, but what I wanted to say is that sometimes lambda can be repeated. For example, lambda 1 can be equal to lambda 2. You may have a repeated eigenvalue using this notation.
Okay, so I guess my question, because I think the reason why we got this is because the indices are the same, right? Like, we got a diagonal because lambda is the same indices as the basis, which is E.
Oh, yeah, you mean that? Yeah.
So my question to you is that, like, are there times when this formation is not a perfect diagonal?
So, okay, if we have a basis of an eigenvector, we can always choose a basis that our matrix will be a diagonal. Okay.
Oh, okay.
But here we kind of made a very strong assumption. I said at the beginning, let's assume that V has a basis given by eigenvector, right? And as you will see later on, not all matrices can have such a basis.
Okay.
Okay, that will leave us to criterion for. So okay, the principle of having a square matrices and finding a basis where it can be written as a diagonal like that. It's called diagonalization. Okay.
Okay.
And you will see that there are some matrices which cannot be written in such a way.
Okay.
And then there's a stronger Okay, so usually the theory of taking an endomorphism and finding some very easy matrix representation of it is called a reduction.
Okay.
Reduction of endomorphisms. And diagonalization is kind of the easiest one you can do, but it does not always exist for any matrices. But there is a more general one, which is called the Jordan canonical form, which is a bit more complicated, but if you work over the complex number, it always exists. So it's a good tool if you want to compute, for example, exponential of a matrix. But yeah. So one application of... So I just want to talk a bit of application. So one application of that is computing solution to system of ODEs. So basically, the problem of solving a linear ODEs can be reformulated as a problem of computing the exponential of some matrices.
Okay.
Okay, so ODE is kind of a very important thing to do to be able to compute the exponential. Another cool application that I want to go through is a classification of conic section. Which is probably the thing that interests me the most. I want to do with you because I think it's pretty cool. So you probably heard of a conic section.
Yeah, we have like basically like a cone, parabola, a hyperbola, and an ellipse.
Yeah. Okay, let me just write all the term plus EY plus.
I still have to practice those, by the way, guys.
Okay. So yeah, so there's kind of two ways of thinking. So there's kind of two ways to think about it. First is you have a cone, and then you have a plane which cross the cone, and then you look at the intersection and you get a shape, right? But an equivalent way of formulating it is that you look at the polynomial of two variables, with which degree that is 2. Okay?
Yeah.
And then you look at the solution to this equation. Okay. Usually, I mean, usually because it's two variable, you will not get a single point like in one variable. You will instead get a curve. Okay, and usually the one that you probably saw is, okay, that's a very bad ellipse. You will have the ellipse, you will have the parabola, and you will have the hyperbola. And okay, those are basically the only three we have. And what we can use the theory of diagonalization. What we can do is we can classify them.
Okay.
Like we can say, okay, if I start with the second degree polynomial, the shape I will get are exactly those three shapes up to some relation. Okay.
Does this classification also have something to do with PDEs? Because I think with PDEs they also talk about the similar thing where it's like hyperbolic, ecliptic, and
there's like something called the symbol of an operator, and the symbol is basically give you like the classification if it's hyperbolic, if it's elliptic or parabolic.
Okay.
So we're gonna do the classification up to affine transformation. So I'm gonna explain it when we do the geometry at some point.
Okay, go on.
But transformation is kind of linear map plus translation. Okay. And we will see that any conic section can be written. I mean, non-degenerate conic section can be written as one of those three. Okay. And actually, what's going to be very cool with the classification is that you see we have the eigenvalue, right?
Yes.
So the sign of the eigenvalue, the fact, for example, if they're positive or negative, is going to tell us which one we are.
Okay.
So it's going to be pretty cool because we're going to have like some equation like that, and just like from computing the eigenvalue of some matrix, we're going to say, oh yeah, this thing doesn't look like an ellipse, but actually it is.
So like when you say the sign tells us, right, is that similar, like I guess like a similar way like how a Gaussian curvature, like if it's negative it's like a saddle, whilst it's like a positive curvature it would be like a sphere? Is it like something similar to that type of idea?
Yeah.
Okay.
Actually, if you look, for example, at surface, then you have something called the I forgot how they call it for the surface, but basically there's something called the Gauss map.
Yeah.
It's called the Wingardium matrix, I think they call it. But basically,
I thought you were going to say Wingardium Leviosa from Harry Potter.
so basically, what it does is you can have a surface, a curved space like that,
right?
And so it's, let's say it's embedded inside of R3, which not all surface can be, but let's pretend we're in this case.
Okay.
And then you have some normal vector to the surface at every point, right?
Right.
But the normals, you know, is a vector norm 1, right?
Right.
So maybe we're gonna add some normal like that, with some p point and some stuff like that. So this is our surface S. Then we have the Gauss map, which is basically the map that take a point on our surface and just map it to its normal. Okay. But as normal are length 1, this is the same thing as mapping into the sphere.
Wait, could you go back for a sec? I was like, so mapping to the sphere, like that part, I kind of lost you there. Like,
okay, so let's say we have a surface, okay? And okay, because it's a curved surface, the normal can change. Okay, at every point you will get a different normal. Okay.
Right.
I mean, if the normal doesn't change, it means you're on a plane. So
okay.
So let's say for example in red I wrote for example the normal for the point P, and I wrote the normal for the point Q. Okay, on our surface.
Right. Okay.
Then we have something called the Gauss map, which take our point P inside of our surface and map it to its normal.
Okay.
So I mean, if you look at normals, you say it's a vector, so it will be mapped to some vector, right? Right. But actually, the normal is by definition of norm 1, right?
Yes.
So it means that actually it's not just a vector inside of R3; it's actually living on the 2 sphere, because it's of norm 1.
Okay.
Therefore, the Gauss map is just a map from our surface to some S2.
So S is representative of the surface, correct?
Yeah, and S2 is just the regular sphere inside of R3.
What about the N with the exclamation point? What is that?
There's no exclamation point, just
it's just two dots, right?
Yeah, it's just the normal at point P.
Oh, okay. So N is the normal and to the surface, and like basically S is the surface, right?
Yeah. So at every point we associate the normal of our surface at that point.
Okay, I was like, why did you write N factorial or something like that?
Yeah.
I got confused. Okay.
And basically, so this is a map from 2 surface, so you can take, so it's a differential map, so you can take his derivative or you can take his Jacobian. Okay.
Like for Jacobian, that's basically a matrix with the derivatives, right?
Yeah. So it's basically we compute the derivative.
Is it partial derivatives or just like a derivative?
So it's gonna be well, we're gonna compute the partial derivative, but we're just gonna get a matrix of we're gonna get a matrix like that. N2 dx1 dn2 dx2, something like that. Okay.
Okay.
Yeah, so okay, usually derivative on the higher dimension, you need a linear map to represent them, and it's a map from, for example, R2 to R2, you need a Jacobian to represent the derivative, okay?
Okay.
And the same is true if you have a space curved surfaces, because locally they just look like a small neighborhood inside of R2, so the same thing works also for those, okay? And curvature, so there's for surface there's like a couple notion of curvature. One is one is determinant of this guy. I think you have to put 1/2 in front of it, but I'm not sure about what is the scaling factor you have to put in front of it. I would have to look up. But this is Gaussian curvature.
1/2 with the determinant of the Jacobian of the normal vectors?
Yeah. And I mean, I'm not sure about the half, but I know determinant times some constant is equal to Gaussian curvature.
Okay.
And if you instead you took the trace, which is like you add up the diagonal, then you get mean curvature.
So like the average curvature, or like around the surface?
Yeah. So I mean, it's called mean. Just basically mean we. Okay. Maybe I should say something.
Yeah.
So this matrix will be a bit special because in the theory you can show that this guy is always symmetric. Okay. and we're gonna talk about it. Maybe we're gonna black box the theorem because it's a bit complicated to solve. But if it's symmetric, then we can always diagonalize it.
Okay.
Okay. And what it's gonna do is when we diagonalize it, it's gonna compute some direction on our surface. Okay, maybe I can do some stuff like that. Okay, this is maybe not the best drawing, but at a point P, it will compute some direction, and it's going to compute some kind of curvature. Those are called principal curvature. Okay.
Why are they called principal curvatures?
Because because they will correspond to eigenvalue of those, and basically those are like the most extreme plates where your space is gonna curve. Okay.
So is the green arrow that's pointing up, is that going off the surface, or is that going with?
They are both on the surface. Yeah.
Oh, okay. So basically, the green arrow is going with the y-axis that you drew, right?
Yeah.
Okay.
If for example you're on something which has positive curvature. Like the principal curvature will look a little bit something like that, and they will kind of both like I mean, there's a notion of curvature for a curve that you can define, but they will both have positive curvature. Okay. And basically, so their eigenvalue is going to be positive, and basically, okay, that's a cool thing. Okay, so you learn about determinant, right?
Learn about what?
Determinant.
Yes, determinant. Yeah.
Okay, another thing which is very cool, if you have okay, maybe we'll just write it with two indices. If you have a matrix which is diagonal, computing the determinant is very easy. Yeah. You just multiply what is on the diagonal.
Right.
So if you have a square matrices, the determinant is just the product of the eigenvalue. So if our two principal curvature are both positive, then the Gaussian curvature, which is the product of those, is gonna be positive. Okay.
Yeah.
And if you think of something which has a negative curvature, which is like kind of a saddle. I don't think I can draw a 2D saddle.
Maybe I could for you. Usually I think of it like something like that.
Yeah. Anyway, in the saddle case, you're gonna have one direction which has positive curvature, and the other direction is gonna be negative curvature. Then when you take the determinant, so those numbers are the eigenvalue of the Gaussian map. I mean the derivative of the Gaussian map. So when you take the determinant, you're just gonna multiply them, so you get that the saddle has a negative curvature.
Sure. Yeah.
Yeah.
That is if it's just a diagonal matrix, right?
Yeah. I mean, at least you can find a basis where this thing is a diagonal matrix. So it's very useful to have a diagonal matrix. Okay. Okay, let me. Okay, so now I can show you that you can do amazing stuff with diagonal matrix. So let's maybe learn how we can compute them. Okay.
Okay.
And you've learned about determinant recently, so we're gonna leverage those knowledge. Okay.
Okay.
Okay. First of all, okay, I will just restate some fact about determinants. So you probably learned that. I mean, you mentioned that last time. If M is a square matrix, we need the matrix to be square in order to make sense of the determinant. Okay. So let's say it's n by n. I mean, it doesn't matter. M is invertible. If and only if determinant of M is not equal to 0, right? You learn about that, right?
Yes.
So if we want to find some eigenvalues for our matrix, we're gonna have to solve this equation, right? M V is equal to lambda V, right?
Okay. Yeah.
I mean, first of all, we should look for the eigenvector, okay? So maybe we can write for the eigenvalue. Sorry. So first quest. How we find eigenvalue. Okay.
Mm-hmm.
So we need to be able to find lambda that verifies this equation for some v which is not equal to 0, right?
Mm-hmm.
Okay. And the way we're gonna do that is we're gonna abuse of this fact. Okay.
Okay.
So okay. I don't know if you know that, but if a square matrix is not invariable, it means it has a non-zero. I don't know if you call it. I think you call it null space, right?
Say that again.
So you know, I mean, I don't know how you call it, but I think you call it like that. I mean, at least you probably heard of like that. Null of M is the set of vector such that MV is equal to 0. Have you heard of that?
Yes.
So it's a null space, but usually in algebra we call that the kernel of our matrix.
Yeah, I've also heard that term as well. Yeah.
Okay, so if a square matrix is invariable, that means that the kernel has to be non-zero. Like they must have something else than the 0 vector inside of it.
Okay.
Actually, that's a if and only if. Like if a square matrix has a 0 kernel, then it means that the matrix is invertible, and if it has a non-zero kernel, then it means that the matrix is not invertible.
Okay.
Okay. So let's see how this fact travel. Okay. So first of all, we're gonna just a little bit reshuffle this equation. Okay.
All right.
So instead of writing that, we're gonna do some very simple manipulation. Okay.
Okay.
Instead of writing lambda v, we're gonna write lambda I is my identity matrix times v.
Okay.
Okay. And now I'm just gonna use some property about matrices. Is that you see I have a v that comes from both sides, right?
Right.
Okay. Maybe first of all I will just move everything on the left. I get something like that, right?
Okay.
And what now I can do is I can factor a v, right? So we would be left with m minus lambda minus the identity matrix parentheses times v is equal to 0, right? So we want to find lambda for which we're able to find some non-zero v that satisfies this equation, right? But it turns out it's equivalent to solve this equation, right?
Right.
But then m minus lambda v is a square matrix. Therefore, a solution to that equation is exactly the same thing as looking at the kernel of f minus lambda identity, okay?
Okay.
And so if we want to find a lambda which has a non-zero kernel, we need that m minus lambda e must not be invertible, right? Therefore, lambda is an eigenvalue if and only if the determinant of m minus lambda identity is equal to 0. Okay? Now that's probably all that, so we're gonna do an example, okay?
So, let's see. I'm just backtracking a bit. So, yeah, so I can see why lambda, like, the eigenvalue can only be that if the determinant is equal to 0, right?
Yeah.
Now, so in this case, does that mean that this combination is not invertible? Like
so you mean that the
m minus like lambda and the identity matrix. that combination would not be invertible, right? Because it's equal to 0.
Yeah, because so the one way is that if lambda is an eigenvalue, it means that there's a vector that satisfies this equation, right?
Mm-hmm.
But then it means that the kernel of m minus lambda e contains this vector, so it's non-zero.
Yes.
Therefore, if the m minus lambda e has a non-zero vector inside of its kernel, it means that the matrix is not invertible. Therefore, the determinant is 0.
Okay. So if there's anything that's non-zero within the null space, aka the kernel, then that means that matrix is not invertible.
Yeah, exactly.
Okay.
Yeah.
I just wanted to connect everything together.
Yeah, because invertible matrices correspond to bijection.
Yeah.
But so if you have a non-zero kernel, it means that you have multiple solutions to a 0.
Oh yeah, because when it's like when you have a determinant that's not 0, it has to be both 1-to-1 and onto. Correct? Like
so if the determinant is not 0, then it's a bijection.
Yeah. So it's injective and surjective.
Yeah.
Okay.
Actually, for a vector space like that, from map to a vector space to itself, it's finite dimensional. Infinite dimensional is a bit weirder. Actually, if you're injective, you're automatically surjective, and the other way also works. If you're onto, you're also into.
Interesting.
Which is something special for linear map, but that's kind of okay. So let's do an example, okay?
Okay.
I will take a non-trivial example, okay? We're gonna take square matrices because you will see real quick what is the bottleneck of those computation, okay?
All right.
So let's take M to be the matrix 1, 2, 2, 1.
Okay.
Okay.
All right.
Okay, so first of all, we have to compute the determinant of M minus lambda identity, okay?
Okay.
So M minus lambda identity is equal to 1 minus lambda. 1 minus lambda, 2.
Mm-hmm.
Okay, so that's one step. And now we're going to compute the determinant of that.
Right. And now we're back to factoring.
So we're going to end up with 1 minus lambda square minus 4. I probably want to write it as 2 squared because I will do a difference of square.
And I think with this, you actually have to solve for lambda as if you were solving for x.
Yeah. So we'll just factor out minus 2. I think I did it correctly. So here we're gonna get. Okay, maybe I will not skip step, even though I really want to.
Whatever's easier for you.
Minus lambda minus 1, right? And now we can just throw out a minus 1 from both parentheses and we get lambda minus 3 lambda plus 1, right?
Alright.
Are we good on the algebra?
Yeah.
Okay. Thus the solution will be lambda is equal to minus 1 and 3. So those are eigenvalues. Okay.
Okay.
So basically, computing the eigenvalue is more like a game of computing the determinant, and the hard part is to be able to factor your polynomial. Okay.
Okay.
Usually that's what is going to be the bottleneck, because when you go to degree 3 and 4, then it's become way more complicated, and when we go after degree 5, then we don't have explicit formula, so even computer will get bottlenecked at this level, and they might need.
And I'm guessing there will be like expressions for like solving for lambda that it's going to be even harder, so it's not just foiling, it could be like a polynomial or something like that, or like a different type of polynomial in some ways, right?
Okay. Yeah. And first of all, I want to use I want to show you some trick. Okay. Yeah. First of all, so this guy, okay, just on the left.
Yeah.
This guy is called the characteristic polynomial.
Okay.
and it plays a big role in linear algebra.
Okay.
And one thing you can see is that our matrix is 2 by 2 there, and we get a polynomial which is degree 2, right?
Mm-hmm.
In general, if you have an n by n matrices, this guy will be a polynomial of degree n.
So I'm guessing like lambda will basically be like will have that many values.
Yeah.
In other words, like if you have like basically a matrix from like n to n by n, you will basically get n number of lambda.
Yeah.
Okay.
Yeah. But then they're gonna have some complication because, for example, if you work over the real numbers, your characteristic polynomial can be, for example, lambda squared plus 1.
Oh.
Then you will not have a real eigenvalue. You would have to go to the complex world to deal with those.
Oh, okay.
And another complication that can happen is that maybe some eigenvalue will be repeated. And this will cause issues. Okay.
Right.
So now we kind of did a good job. We find the eigenvalues. Okay.
Mm-hmm. Mm-hmm.
Now we can compute the eigenvector. Okay. If we go back to the analysis I did before,
mm-hmm.
I said that solving the equation mv is equal to lambda iv, right?
Yeah.
Is the same thing as computing the kernel of m minus lambda e. So, for example, the equation mv is equal to minus v. Mm-hmm. Okay, the solution of those are exactly the kernel of m plus identity.
Okay.
And the same is true see for 3v.
Mm-hmm.
But instead I'm gonna need to solve for m minus 3i. Okay?
Okay.
So what was the matrix I chose at the beginning? 1, 2, 1, 2. 1, 2, 2, 1, okay. Okay, now that's usually the part we have to work.
Mm-hmm.
Okay, let's do for the first one, okay?
Yeah.
So for the first one, so we said lambda is equal to minus 1. So I'm gonna just add the identity to that guy, right?
Yeah.
So I'm gonna end up with 2, 2, 2, right? Okay.
Okay.
And now we want to solve the equation like that, okay?
Okay.
So there's like kind of a standard way, which is using Gauss-Jordan elimination to do that. I think you know about it.
Yeah.
Yeah. But usually in 2-dimension, you can just look at the matrices and figure out what's going to happen. So in these matrices, we have the first 2 columns are the same, right?
Mm-hmm. Yeah.
So if I take, for example, if I take the first column minus the second column, I will get 0, right?
Mm-hmm.
Which is exactly the same thing as picking this vector, right?
Right. Yeah.
So this is why it's easy to see 0. Okay, and actually, so this means that the kernel of m plus I has to be of dimension 1, right? At least, because we found a vector, right?
Right.
But m minus 3i must also have dimension at least 1. Okay? Because we check and we saw that the determinant is non-zero, right? We check and we saw that m minus 3i determinant is 0, right?
Mm-hmm.
Therefore, the m minus 3i must not be invertible, therefore the kernel must be non-zero. So it has to be at least dimension 1.
Okay.
But then it means that m plus I, the kernel of m plus I and the kernel of m minus 3i are at least of dimension 1.
Right.
But the total space is of dimension 2, so the most it can be is dimension 1, so the dimension is 1.
Okay.
So the vector, I mean, you can do it Gauss-Jordan, but I like to do this kind of funky stuff whenever I can. Because Gauss-Jordan is sometimes a bit painful to do, so... So the kernel of m plus I is generated by So it's given by linear combination, just by a multiplication of this guy by some constant. Okay. My apology.
It's all right.
And so that computes an eigenvector for our matrix. Let's do the second one. So now we're gonna do for lambda is equal to 3. So we're gonna get kernel of m minus 3i. So we said that m minus 3i, so this guy was 1, 2, 1, 2 to 1, right? So it's gonna be minus 2, 2 minus 2?
Are you just writing the matrix?
Yeah, I wrote m minus 3i. Did I screw something up?
I think it was just, let's see, m was 1.
Yeah, that's right. I just subtract 3 from the diagonal. That's fine. Okay.
Yep.
And now we need the kernel of that guy, but again, it's not very hard to find a vector which is inside of this kernel because the first column is just minus the second one, right?
Right, yeah.
Therefore, I can just take the vector 1, 1, 2. It's inside of the kernel of that. Again, you can always use Gauss-Jordan, but sometimes it's a bit just faster to just look at the matrix and see if you see some obvious linear combination. If it's a 2x2 matrix, it's always easy to find because there's only two columns. Therefore, the only linear dependence they can have is that one is a multiple of the other, right?
Mm-hmm.
So usually by 2x2 matrices, you can just like do it, as I say in French, à la louche. You can just like look at it and find some solution. But
what does that mean?
Just like kind of, I don't know, like raw dog it a bit, just looking at it and see, oh yeah, I see the solution.
What was the term? À la louche?
À la louche.
Interesting. No, because like I remember an anime I used to watch called Code Geass. The main character's named Lelouch, so it's just funny. So it's called à la louche.
So we found.
Mm-hmm.
1 minus 1 is an eigenvalue of 1, and 1, 1 is an eigenvalue from minus 3? No, for 3, I think. Oh, it's 3, yeah. Eigenvector, sorry. Oh, so this guy is lambda equal minus 1, I'm sorry. Alright.
It's alright, Major Finger. Welcome to the chat.
Okay, and basically from that we're done. I mean, almost. Usually what you want to do from that point is that you want to write some... So you have a basis, right? But usually, for example, if you want to do computation, usually you will have some vector, right?
Uh-huh.
Usually in most contexts, it will be given in the standard basis, okay?
Okay.
Something like that.
Yeah.
But now you have this vector, now you have another basis, right?
Right.
Which is those guys.
Yeah.
So you need a way to convert this representation to so this should be a minus to a new representation in our new basis. So you need a matrix called base change matrix.
Okay.
Basis change matrix.
So we need a certain I guess we need certain coefficients to make it possible.
Yeah. And the way you do that is first of all you kind of do the easy problem.
Uh-huh.
So you can sort of imagine that you can map the vector 1, 0 to the first vector of our basis,
Okay.
and you can map the second vector 0, 1 to our second vectors. Therefore, you get a matrix of this form. Okay.
Okay.
While the column are just our eigenvector. Okay.
Mm-hmm.
And now what you're gonna do is you're gonna invert that guy.
Okay.
So what is this guy's doing? So let me call the standard basis B0 and B1 and B2,
Mm-hmm.
and maybe let's call our new basis E1 and E2.
Okay.
So what we are going is that what this matrix doing is it's mapping B1 to E1, and we're mapping B2 to E2, okay?
Mm-hmm.
Yeah, and we would like to be able to do the opposite. So what we're going to do is we're going to compute the invert of this matrix, okay?
Okay.
But I will probably not do it now because it's a bit completely expensive. It's not too expensive, but I mean, I don't really like to compute inverts of matrices, so maybe...
Yeah, same here.
I will not too focus on that. For 2x2 matrices, there is like an easy formula with the terminal that you can use.
Yeah.
But usually it's a bit harder. But I just want to focus on the first part, which is compute eigenvalue and eigenvector.
Right. Okay.
Okay. So maybe we can do another one. Okay. And this one I will maybe let you do it, but I will guide you a little bit. Okay.
Major Finger basically says on Twitch, they say it's a chore to do linear algebra with when it's not abstract. Right.
Yeah, unfortunately, you're like, oh yeah, in theory, like everything is so easy, and then you do computation, it's like, oh no. I was trying to compute some rank of some matrix in this weekend.
Uh-huh.
I was like, oh yeah, I just need to compute the rank. And I'm like, the matrix is like is a matrix 48 by 48.
Mm-hmm.
I'm like, oh yeah, I'm not computing that rank by hand.
So you're saying that doing proofs with linear algebra is a little bit easier than doing computation with linear algebra?
Yeah.
Interesting.
I mean, for linear algebra, I mean, at least when you do it by hand, you can probably do at most like your 4x4 matrices before that becomes like kind of a chore.
Yeah, like after I learned like the basics, like I think like when it came to like determinants, I no longer did it through hand. I basically just used the calculator if it didn't ask for the determinant directly. Yeah.
I mean, I can tell you that this weekend when I wanted to compute the rank of the 48 by 48 matrices, I didn't do it by hand. I mean, just the logistic of writing a matrix with 48 entries.
Like before
on the chalkboard.
Like before, when I was learning linear algebra, I feel so disappointed because I couldn't do it by hand. But then when I started understanding like basically the basics, I was like, okay, I no longer feel guilty by just typing it all in the calculator anymore. Like, you know, when you do is it Gaussian elimination? Is that what it's called? Like when you basically try to turn it into an identity matrix? Yeah, like for me, I would feel guilty not being able to do it when the section required that. But then, like, when you had to do it for other problems, I didn't feel guilty, like, using my calculator anymore. Before I did, because I was like, oh my gosh, I can't do this in my head. But then I realized it's just very tedious to do it.
Yeah. Okay, I'm looking you for a good example. Okay, this won't work. Okay.
Major Finger says on Twitch, I was once given a 4x4 matrix to invert. Took me 30 minutes and I still got it wrong. Yeah, that's the thing I don't like about like doing those things, because when it comes to doing a lot of arithmetic in your head, that's the reason why I don't like doing like 3x3 or 4x4, because I know I will mess something up.
Yeah, I mean, when I was a teen in linear algebra, I did some very funny computation on the chalkboard.
There was like a determinant problem that I was doing. I forgot what it was asking for, but I had to basically, because I think when you're doing certain determinants, you have to take into account what you're doing to the matrices when you're trying. What's the what's the section where you have to either convert the bottom triangle to zeros or the bottom top to zeros? Sascha?
This is Gauss-Jordan elimination.
Yeah, like when it came to that, I had to basically do. I think it's involving with the determinant, and I think if you switch 2 rows, you have to multiply by 1. I mean -1, and then when you have to do any other operation to manipulate the rows, so it's like you turn the zeros, whether it be the bottom triangle or the top triangle. You have to multiply it by the determinant you're doing it with.
Yeah.
Like I didn't know that. I thought like when you switch the rows, you had to turn it into -1. You had to multiply it by -1, but it didn't tell. But the section I read, it was like it didn't explain that you have to do every single manipulation that you did to the matrix onto the determinant that you're doing it to.
Yeah.
And I was like trying to think about like how did they get this answer, and I was like trying to figure out like was it my manipulation, was it the way I did the matrices, did I do it wrong? And apparently I just missed a step, which is like multiply every operation you did onto the matrices onto the determinant that you got. And I was like, oh, that's what I was supposed to do.
All right. So here's the example I want you to try.
And what is our objective with this one?
So we want eigenvalues and eigenvectors.
Okay.
And usually you want to do it eigenvalue first and eigenvector second.
Okay. So in this case,
Yeah, you're supposed to put the V on the right, but...
oh, right, yeah. Oh wait, which
only on the last one.
Oh, on the last one, okay.
Yeah.
Because I was like, isn't that the way you wrote it last time?
Oh, did I?
I don't remember. No, I think it's just I'm so used to it being like single numbers when you factor out. I'm so used to putting the number on the...
Oh, yeah. Yeah, for matrices, like if you had like a column vector on the left, like for example, you use like computer, it will complain because they don't have matching rank.
Okay. So we got this. Oops.
Yeah, that's a really cool matrix. Yeah, we like triangular matrix.
Yeah. Let's do this one, and then this one.
Oh, you don't need to do that, by the way.
Oh, you don't want it. Oh yeah, that's right.
Because we only have a
We
zero,
already,
so we
yeah, we have the. So in this case, basically lambda is equal to 3, and in order for that to be 0, to make sure that that's -1. Okay.
Yeah, what a champ.
And now we have to do the. So now we actually have to get the vectors now.
Yeah.
Eigenvectors. Okay, so now.
Oh.
Let's see. I'm trying to remember. Are you?
I think I lose. I lose the page.
Oh, you lost the page?
Oh no, it's good. I see it. Okay.
Oh, you got it? Okay.
Oh, I see it at up to some point. I don't see the newer stuff.
Oh, the newer stuff?
Yeah. Maybe I can just try to reopen it and see if it works. Even though I think we have no hope for that, so let's see.
Okay.
Yeah, I see the. No, I don't see the new stuff.
Okay. So should we make a new one?
Yeah, I think we should. So
Okay.
maybe just note the eigenvalues. What were they? -1 and 3?
-1 and 3, yeah.
Okay. I will just write them down Discord.
Do you have the original matrices you had?
Yeah.
Okay.
I do.
Alright, so should I just like refresh the page and just send you another link?
Yeah, send me a new link
Okay.
with a new page.
Okay, so how do I renew this? Maybe if I reload the page. Just bear with us, guys. We basically had like some technical issues.
All right.
Can you see everything now?
No, I can't. I think we need a new canvas.
Okay.
What?
Let me see. Maybe I have to end the session and then restart. So stop session. Okay, there we go. I was like, why can't I reset the thing? Okay. Send that out. Alright, there we
Alright.
go.
Okay, so
So
do you want me
had-
to rewrite the matrix? Oh, you already have.
Yeah, you just rewrite the matrix.
Okay, so M was -1, 2, 0, 3.
And the eigenvalues we had was 3. Okay. Alright, so originally our equation was eigenvalue of... No, not V. Alright. So now we have to do this. That's all equal to 0. So minus, I guess we'll make that +1. So thus we have 0, 2.
Oh, yeah. Hold up. Yeah, this is supposed to be a minus.
Oh yeah, right. Thank you. Okay. Now. So let's see. So the eigenvalues, and then we got this. And I think we also need V in there. No, I'm missing a step here.
So, in order to find some eigenvector for a first eigenvalue, we need to compute the kernel of that matrix, right?
Oh yeah.
So here we're gonna cheat a little bit because we know we have two eigenvalues. So I mean, we can do basically the same as I did before. So it means that those kernel has to be at least dimension 1, but there is only 2 of them. Therefore, it has to be exactly dimension 1.
Exactly.
Therefore,
1.
Yeah. Therefore, we just need to find one eigenvector for each of those matrices, and we're good.
Okay. So. Because when we take the kernel, we basically have to make it equal to the 0 vector, right? So.
Yeah.
Okay, so. Oh, okay. So basically, what I have to think about is. It's supposed to be this formation, right? Like.
Not this guy, not M on the V, but.
No, I'm just using M as an abstract matrix.
Oh yeah.
I'm just like it. I probably should have wrote K or something, but yeah, something like that. So basically, it's like we're taking this matrix and like multiplying it by V vector to get 0, but we're just trying to figure out this part, right?
Yeah.
Okay. So we have V 0. So basically, V has to be a certain. So it has to be a. This is 2 by 2, so it has to be 2 by 1. Okay, I don't know why am I getting like stuck here.
It's okay.
Because I feel like I know what to do, but at the same time I'm like, wait, why am I blanking out now? Thank you for the follow, Puika. Hopefully I pronounced your name right.
So the way I like to think about them is that we're trying to solve. So we have column. So we have our 2 columns here, right?
Right.
And we have. I mean, we multiply by some column vector AB. But what this guy is gonna do is gonna just take some. So A is just telling us we're gonna take A times the first column.
Yeah, that's what I was thinking too, actually.
And B is gonna take B times the second column, and we just need to find one vector, one combination of A and B, which give us 0. other than the obvious one, which is a and b is equal to
It's
0.
to 0. Yeah.
Yeah, but here there's a one which is kind of easy to find. Is take b to be 0 and take a to be like 1.
Mm-hmm.
Because the first column is 0, so no matter what
Yeah.
a you put, the first column will just kill it. So
Yeah. And then we're left with oops.
the other way around, yeah.
And that's 0. And then we're just left with double 0 at that point. So it's 0, 0.
Yeah.
So one eigenvalue would be at
Eigenvector.
-1. So just put e.
Oh yeah, okay.
0, 0.
It's not 0, 0. Yeah, so you found that a is equal to 1 and b is equal to 0 is a solution, right?
Mm-hmm. Oh yeah.
So it would be 1, 0.
Yeah, 1, 0, right.
Yeah.
Is it okay to make guesses like that?
Yeah.
Okay.
I do it all the time.
Okay.
I mean, the only exception where I use Gauss Jordan is for like the 3x3 matrices.
Oh, okay.
Sometime, I mean, most time I will try to guess the solution, but if there's like some very complicated linear relation, then I will use Gauss Jordan.
Hmm. Okay. Alright, so I don't think this trick is going to work.
No. But we can look at the column and say, are these similar?
Let's see. Because we want a4 plus b2 to equal 0. And these are just going to be 0, so negative. So if we minus b2 a4, so that would equal 2a. So the vector basically has to be 2a, b.
So you have to fix a constant for either b or a.
Yeah.
So just make 1 to be equal to 1.
So basically, let's say b is equal to 2. And if that case, then a... No, that wouldn't work. So we can make b equal 1, and then a can be equal to a half. So if that's the case, I mean that works out.
Yeah, that works.
So e2 would be, and if this is 2, multiply that, then yeah, then it'll be 1, 1.
I think you have a typo. Okay, this part is not okay. What you should have instead is that you should have a to a.
Right, oh yeah, that's right. So basically,
So probably
it should be like two. It should be like 2.
Yeah. Probably the easiest thing to do is to take a to be equal to 1.
Yeah. Okay.
So what we found is that lambda is equal to -1. You found the eigenvector 1, 0. And for lambda is equal to 3, 1, 2, so is that?
Oops. I don't
Yeah,
know why
okay.
I'm writing a triangle.
Peter, do you allow me to show you one quick example?
Sure.
Alright, I will do it quickly. Okay, so in the 2 cases we did before, we were able to diagonalize it because we were able to find in both cases we were working over 2-dimensional and we found 2 vector, which form a basis. So we were able to diagonalize it, but I will show you an example which doesn't work here.
Okay.
Let's take the matrix M to be 0, 0, 0, 1.
Okay.
Okay, I will show that this matrix is not diagonalizable. Okay. And so, okay, let me do the procedure. So first of all, I will compute the eigenvalue. So it's going to be M minus lambda identity.
Okay.
So it's going to be minus lambda, 1, 0. Oops, I forgot. I guess I'm going to put some square line there. Okay, but this is a triangle matrix, so I just need to multiply the diagonal. So I just find lambda square, right? And here you come to one case where you can have a problem with finding diagonalization is when this polynomial has repeated roots.
Right.
So there is only one eigenvalue. So if you have only one eigenvalue like that for a 2x2 matrices, it doesn't mean that the matrix is not diagonalizable, but there's a chance that it is not.
Okay.
And here we will see that it's not possible because so if M is diagonalizable, right? It would mean that okay, maybe I will use R2. So it would mean that the eigenvalue so the eigenvalue, you agree with me, are just the kernel of M minus 0 identity, right?
Right.
In this case, will just be the kernel of M, right? So those are exactly the space generated by the eigenvector.
Okay.
But if M is diagonalizable, it would mean that the kernel of M should be the whole thing.
Okay.
R2 should be equal to the kernel of M. That's the only way we can get the basis.
Okay.
But if that's the case, so M is a map from, okay, I will abuse notation, I will write as a map from R2 to R2. So if the kernel is the whole space, right?
Yeah.
It means that whatever vector I give it to my linear map, it will give me 0, right? So this would imply that M is equal to 0, right?
Right.
Is a 0 matrix.
Yeah.
But that's not the case. As M is equal not to the 0 matrix, but almost, is equal to that. Thus M is not diagonalizable.
So for the kernel, before you wrote M minus 0 I, right?
Yeah.
So so how did we get the 0 again for lambda?
Because I solved the I was looking for the eigenvalue, right?
Oh, okay, yeah.
And I found the polynomial is lambda squared, therefore the only eigenvalue are 0.
0 because you basically square 0. It's like basically you're squaring. Whenever you square a number, it has to be like that square. Otherwise, it would be 0 if it was equal to 0.
Yeah.
Yeah. Okay, that
so,
makes sense.
Yeah. And if I use Gauss Jordan, I can also directly show that the kernel of M is one-dimensional. I can also do that instead of using the argument I used.
So this is when you cannot do it, right?
Yeah, here we cannot diagonalize because we don't have enough vector to do it. Like there's not enough eigenvector to form a basis. Therefore, we cannot diagonalize M.
Is there a branch of math where you can do it, or this is like completely like you can never get an eigenvalue and eigenvector from this?
So you cannot get another eigenvector from that, but there's something related, which is the Jordan canonical form, which I mentioned earlier, which is like a more general version of diagonalization that's worked for any square matrices as long as you're willing to work over C.
Okay.
But yeah, even over R, this guy would have would have a Jordan canonical form, but it will not be diagonalizable.
Oh, okay, I see. So it has to require a more rigorous way of solving it. Okay.
Yeah, and usually the way you do that is that you have. So first of all, when you do Jordan canonical form, what you do is you first try to diagonalize it. If you see that it fails, it means you don't have enough eigenvectors. So what you do instead is you look at something called the generalized eigenvector. Which is basically, instead of looking at the kernel of M here, we're going to look at the kernel of, well, I guess I will write in general, we're going to look at the kernel of this matrix square.
Okay.
And this is a space of generalized eigenvector. And if that's not enough, then you're going to go to the higher power.
To a third?
Yeah.
Oh, okay. Yeah.
And so on.
That seems tedious.
Yeah, and at some point you will have enough eigenvector. Usually the degree you go at most is, so you see when we do this factorization, M minus lambda identity. So if you look over C, everything will split up. So it will be lambda minus lambda 1 times some exponent.
Yeah.
Something like that. And usually the highest power you have to go is whatever, like, for example, this is lambda 1, is what is the multiplicity of the root for the polynomial.
Okay.
So that's the name of the thing. So the dimension of the kernel is called the geometric multiplicity of an eigenvalue.
Okay.
And the algebraic multiplicity, which is like just how many factor you have it in the factorization, is called the algebraic multiplicity.
Okay.
And usually diagonalization fail when those two numbers are not equal.
Alright.
For example, in the previous case, the geometric dimension is the geometric multiplicity of our eigenvalue 0 is dimension is 1, but the algebraic multiplicity is 2. Therefore, we have obstruction to diagonalization.
I see. Okay.
Okay.
Right.
Yeah. So I think I can send you like some page in the what is called
the Discord.
Linear algebra done math. Linear algebra done right. Probably any linear algebra textbook will cover some of them. But if you want to do like some exercise,
sure.
Yeah. Because it's more like computation, but yeah.
Yeah. Okay. Sure. Yeah. No problem.
Did you like that?
Yeah, like it makes me feel like I'm understanding a little bit more about eigenvalues and eigenvectors a bit better. So, like I remember when I finally understood, or at least like comprehended a little bit about linear transforms. I was like, oh, okay, because like before I would think like it's so foreign to me, but then when I started doing it more, I was like, oh, okay, now I get what's going on here. I think what I liked most was that basically just multiplying a matrix by a vector, like simply, like basically like a 2 by 1 vector and a 2 by 2 matrix. I think that's really cool because it's like, if I have like, I think one of the fun exercises is like, when you get the vector for the, I think for the vertex of a shape like a square or something, and then you transform that into with a matrices, like it stretches the square or something like that. I find that very fun. But thank you, Sascha, for showing me more about eigenvectors and eigenvalues. That actually helped me a lot. and like giving me a problem to work with, because I think that helps solidify it a little bit. So I got to work on the eigenvector part, but I think like I feel like I have a better clue on how to figure it out. So thank you very much.
I think the theory of eigenvalue and eigenvector is quite, it's quite like it's kind of a good theory to show to students, because like it's not very abstract and you can do like a lot of computation to figure out what is going on in the theory, right? Mm-hmm. So I guess I hope the computation side will help you understand it a little bit better.
Yeah, it actually helped me a bit, because I know that eigenvalues and eigenvectors are important, especially when it comes to like Schrodinger's equation. So there's like a similar notion for operator, and that's what you use for PDEs. Like for example, Schrodinger or heat equation, you can decompose the differential operator into like eigenfunction and eigenvalues, and make your life a bit easier. Okay, but like I said, Sascha, thank you very much. If you guys want to check out Sascha's content, he's also streaming on Twitch. I put it in the chat. For Twitch. In addition, if you want to check it out, if you're watching this on YouTube, the link to his Twitch will be in the description down below.
Thank you.
Yeah, so Sascha, is there anything you want to say to our global audience before we depart for today?
Drop the bell, it's been too long. I don't remember all the.
So like if you guys like math, physics, and you're watching this on YouTube, like hit the sub button. Like if you're watching this after the live stream, drop a comment down below and like the video. It really helps me out and inspires me to keep doing more math content for you guys. In addition, if you're watching this on Twitch, for people that followed, thank you for following. But if you haven't followed yet and you want to follow and keep up with the content that we're putting out there, and we'll probably have Sascha on again, because he's just a really awesome mathematician himself. He's working on his PhD. He's going to be working on his PhD pretty soon, so like we're cheering for him. But yeah, drop a follow if you want to keep up with like what we're planning to do in the next stream, because I think like there was a video I actually sent you, Sascha, about forgot his name. I always forget this mathematician's name, but he's a really well-known mathematical physicist. I think it's Gabriele Carcassi. I think that's how you pronounce his name. If I mispronounce that, I apologize. But like, I love the video that the video I sent to Sascha was basically you can find this video on YouTube. If you guys want to know what that video is, like leave a comment down below and I'll probably post it for you. But like he was talking about how we need physical mathematics, and I thought that was something that I've been trying to do on this channel. Just trying to develop my own way of interpreting the physical world mathematically, as well as interpreting like physical things in a mathematical way. So Sascha like basically has like experience with like algebraic geometry, as well as like what other fields have you done, Sascha?
I mean mostly algebraic geometry, but I started in differential geometry.
Because you seem to know more about like the mathematical structure of physical like physics ideas, and I find that very inspiring, actually. Because like you don't really like physics as much, but you know a lot about it, which is really, really interesting to me.
Yeah, it's because my field has a lot of application in physics. Yeah. I mean, in some branch of physics, let's say.
Yeah.
Therefore, there's like kind of idea that leak out in mathematics, so you kind of heard about that.
Yeah, because like for me, I don't know anything like say like phase spaces or anything like that, so I'm still a long ways to go before I can go into the harder maths. In fact, like I'm still struggling with the baby maths of what you need for physics. So, like I'm also still trying to train myself a little bit by little. I don't try to like do like a textbook, like open up a textbook and do 100 problems, but I try to open up a little book and basically see like how many physics problems I get wrong and how many I learned from, and how many I can basically apply, and how many I get right also, because it shows where my placement is in both subjects. But yeah, so Once again, guys,
I-
thank you for. Yep, go on.
I just want you a good sheet of exercise.
Oh, okay. Let me see here.
Oh, you want me to send you? Okay. I mean, I will probably mark you some exercise because some of them are not very computation, but I will send you the one which require computation.
Okay, I'll definitely check it out. Thanks for sending that to me on Discord. I will definitely post these. If you guys want to join our Discord server, if you're watching this on YouTube, it's in the description down below. I will definitely post these, the page that Sascha posted to me. So I will post that in the assignments from stream section. So if you want to actually try to practice those, you're more than happy to do so. But yeah, so Sascha, once again, thank you very much, and I will try to catch you like sometime later.
Yeah. See ya.
Alright, take care. Alright guys, so basically that will conclude today's stream. We will be back tomorrow, so what we will do tomorrow, who knows? It depends on what inspires me, whether it be like physics related or math related, or maybe it'll be a mixture of both. But yeah, so always remember guys, everyone is precious. You guys are just as precious as everyone else, and I will see you guys in the next stream. So take care guys. Bye-bye.